Hello, everybody, and welcome to the Consulting Specifying Engineer webcast, Trade Secrets of Standby Power Systems, sponsored by ASCO. I'm your moderator, Michael Ivanovich, president of the Ivanovich Group. And in today's webcast, we'll cover design and specification issues associated with standby power systems with emphasis on specification. Specifying systems so that they are installed as designed and holding that spec against contractors who may want to make substitutions that compromise the safety or performance of the system is not only critical, it's an art. So CSC is proud and excited to provide specification trade secrets of two members of its editorial advisory board, Keith Lane, president of Lane, Coburn and Associates in Bothell, Washington, and Ken Lovorn, president of Lovorn Engineering Associates in Pittsburgh. This webcast will last approximately 60 minutes. Ken and Keith will present for about 25 minutes apiece, and then we'll take questions from the audience. I'll introduce our first speaker, Ken Lovorn. Ken Lovorn is president of Lovorn Engineering Associates. He has 40 years of design and engineering management experience with architect engineers and consulting engineers and designing, His experience includes designing electrical systems. He is also a member of Consulting Specifying Engineers Editorial Advisory Board, and he has just started a new blog at cscmag.com called Engineers Cooking, which I encourage everybody to check out after the webcast. Ken Lovorn, the podium is yours.
Thank you, Michael. Our first trade secret we're going to talk about today are the sound attenuating characteristics necessary for critical environments where you're installing a generator in a very, very quiet environment and your typical weatherproof enclosure or just putting a sound attenuating box around it doesn't necessarily work. The first issue that has to be addressed is the mechanical noise that travels through the air from the engine and generator set. The second is the vibration transmitted to the structure, and that vibration passes directly through the integral snubbers that's between the generator and its skid base. So that handles the gross vibration, but it really doesn't handle the vibration that creates a lot of noise in a building. The third one is, of course, the combustion noise that comes out through the exhaust pipe. On that particular one, just a standard muffler works okay, but when you've got a critical environment, it doesn't work very well. So if you've got all these in place, you can then get noise transmitted through the system connections, where you're connecting the electrical or piping systems in. And with all that in place, you need attenuation on your sound attenuating enclosures, and that varies, which we'll get into earlier or later, that varies from 25 to 55 dB. The more attenuation you need, obviously, the more it costs, and the larger space requirements. As the sound attenuating enclosures require more attenuation, they get bigger. So we'll consider each of these as we go into the slides later here. And I'm still... there. Okay, the typical sound attenuation paths are shown graphically here, where you have sound leaving the generator out into the air. You have the sound coming out of the generator exhaust. You have the sound being transmitted into the structure. All these have to be mitigated for you to be able to maintain a quiet environment. This slide shows the relative cost and the relative size based on the amount of attenuation that you're trying to achieve. As you note, at 25 dB, the cost is fairly nominal. As you go up to 35, 45 dB, it rises a bit. But when you get to 55 dB, that's pretty much the state of the art, and you're looking all of a sudden at $750,000 to quieten a 1 megawatt generator with 55 dB of attenuation. Likewise, as the attenuation requirements go up, you have an increase in the size of the box because the attenuators, particularly on the air intake and exhaust, get larger, and plus the attenuator enclosure is just simply thicker. Addressing the structural noise attenuation, the vibration isolators on the generator set are good just so that you don't get a lot of the gross vibrations. So you have to do something else. The first step is to put vibration isolation springs between the skid base and whatever the structure that you're mounting the generator to. You need at least 2 inches of compression on each of the springs. If you get a spring that only compresses, say, a ½ an inch, it will transmit more vibration, so you need a spring that's fairly compliant. The second thing is you have to put in some kind of cork neoprene vibration isolation pad. The vibration isolation springs take care of the low frequency, but they don't do real well with the high frequency vibrations, and so you put the neoprene isolating pads to take care of the high frequencies. Once you get those in place, you still have opportunity for vibration to pass through those. It's not nearly as much. But if you put in an inertia pad below the generator set that weighs at least 1.5 times the total weight of the generator, you start having an opportunity to slow down a lot of these vibrations because you just can't pass the vibration through this big mass of steel and concrete. Once you raise the inertia pad above your structural base, put it on another set of vibration isolating springs, now you start getting an opportunity to get some real isolation from the structure. If you size the inertia pad large enough for the enclosure to fit over the generator and directly against the pad, that really gives you your best isolation from getting any vibration. If you size the attenuating enclosure large enough to actually enclose the inertia pad and go down against the structure, the enclosure gets significantly larger, and so it's really more economical to put it against the inertia pad. And then finally, you need to seal any air gaps between the inertia pad and the sound attenuating enclosure with the sealant recommended by the manufacturer so that you seal every little teeny tiny air gap. This is a picture of a typical vibration isolating spring. It has an integral waffle pad, and this is called a restrained vibration spring because it has an enclosure around it. It has a little more stability than the unrestrained spring. So these are a little better as far as maintaining the stability of the unit. The second consideration is ventilation and combustion air. You have to maintain adequate cooling intake and exhaust area. The louvers typically are in the 50% free area. So if you've got a 4x4 louver, its free area is only about 8 square feet rather than 16. So when you're doing your calculations, you have to take that into account. You want to leave your velocity of your air as it passes through the louver something under 1,000 feet per minute. My typical target is around 800 so that you don't get a lot of pass-through of rain as you're bringing air into the cool the generator. You need a louver that closes tightly, particularly in colder environments, so that you can retain the heat within the room. And then the path, both for the intake, cooling air, and exhaust air, needs some kind of serpentine path. It needs to make several 90s so that there's no direct path for the sound to pass from the generator to the outside. You can also put in sound attenuating liner in that to further absorb the sound. when you're doing the calculation for the intake, you need to make sure and add adequate area so that you get your combustion air volume included in that, because if you don't, your combustion air will take away from your cooling air and you end up without adequate cooling. And finally, when you finish with all this, you really need to check very carefully with the generator manufacturer to make sure that you meet their specific requirements for their unit. If you've got a 1 megawatt generator set and it's just a generic one, it may be completely different from the generator set that you've actually designed around. And when you're reviewing the specifications, you need to look at those air volumes to make sure that they've been accommodated. This is a picture of a sound attenuating enclosure. If you note, on either end of the enclosure there is a curved area. Those are the air intake and exhaust louvers that allow the air to enter without having a direct path. The exhaust noise attenuation is handled by a muffler or a silencer. The industrial class silencer ranges between 20 to 25 dB of attenuation. When you go to residential, the residential silencers are somewhat quieter, and so you get about 25 to 30 dB of attenuation on those. When you have low density housing, and like in rural areas, it's even quieter. You need more attenuation, and you can go to the critical class, which is between 30 and 38 dB of attenuation. And then finally, the supercritical or hospital grade of attenuation, you can get 35 to 42 dB of attenuation. Some manufacturers provide a fifth category, which is provides really the maximum attenuation available. It runs between 35 and 50 dB according to how large the unit is and how closely it's designed to the system. Here's a typical silencer. This is a input in and an input out of the cylinder. You can get side inlets and exhaust. You can get them puck shaped so that you can have a compact installation, and they work out very well. System connections. All of your system connections need to have some kind of flexibility so that you don't pass vibrations. You've got a fuel supply line and a fuel return line that are generally hard piped. You have the electrical power connections where you connect the power generated by the generator out to the emergency system. You have the control connections, which provide the start signal from the transfer switch and the remote annunciation. And you need to provide all these with some kind of flexible connection. The best that I've found is the wire braided neoprene hose or pipe type system, and it needs to be about 10 times as long as it is in diameter. So if you've got a 4-inch diameter pipe, it needs to be about 40 inches long. You provide extra length and flexibility so that the vibrations both horizontally and vertically are not passed through these connections. And here is a typical, this is actually a typical pipe, but the conduit looks very, very similar. This is a slide showing really a section through a completed installation. You've got the generator inside, you have the silencer inside the sound attenuating enclosure. The only exit is either horizontally or you can take it vertically through the roof for the exhaust. You've got a serpentine path so that you don't have any direct noise path for your air. You have the inertia pad mounted on springs. You have the generator mounted on springs on top of the inertia pad. And then you have all the connections for the air and, for the fuel and fuel return and electrical connections that pass through the pad. You try not to run those through the sound attenuating enclosure because it makes maintenance more difficult. It makes it difficult to take the enclosure off. You have to disconnect everything. The second item is successful load assumption using transfer switches when you're attempting to pick up a load with your generator set. If you've ever had a properly sized generator fail to assume load, or had the generator output waveform distorted so that loads were affected, if you tried to add load and had a generator not accept the load, or if you've had motors trip offline when transferring, the problem is you probably have improperly sequenced transfer switches. There is a solution. The issues that you have to address are the time to the first transfer, which means from the time power fails until the generator starts, comes up to at least 90% voltage and frequency, and the transfer switch transfers. The time in between the first transfer switch operation and the subsequent transfer switches, and the sequence of load, which ones you want to come on first, and in what order would you like to have those begin. On the initial transfer time, National Electrical Code is mandating that the life safety loads, such as exit lights, egress lights, and other safety type equipment are online within 10 seconds of the power failure. In hospitals in particular, there is also a National Electrical Code requirement that the critical branch, which are loads that make sure patients stay alive, essentially, those also have to come on in 10 seconds. The equipment branch in hospitals, such as air conditioning for sensitive areas and things like that, where the motors are larger, they're allowed to come on after the 10-second period. The time that is necessary to allow the generators to come up to full operating speed for the 1800 RPM standby generators that typically are specified, those should be able to start and assume load within 7 to 8 seconds. If you've got larger, lower speed generator sets, and some of the older units are the 1200 RPM or 900 RPM units, they have a much larger mass. They're intended for prime power applications, and they take much longer to start and assume load, so they've got a much larger rotating mass. Natural gas generators, while they still are fairly large, they really don't have quite the same rotating mass, but they do take longer to come up to speed. So sometimes the natural gas generators in the larger sizes become somewhat problematic. We'll look at that a little bit more later. The allowance for complete wind down for high inertia loads, you have to be able to allow some timing so that if you've got like an induced draft fan or something that has a high inertia and continues to spin, you want to make sure that it's completely stopped. It has residual magnetism in the rotor, which causes reverse EMF to be generated. And if you close the transfer switch between this motor and the emergency power, when the motor is still producing this reverse EMF, you end up potentially with a phase-to-phase fault, because you can be out of phase between the emergency power and the motor generated reverse EMF. So you get a fault condition. That has been shown to actually twist steel shafts in half. So it's very damaging to the equipment. The other load that has similar kinds of characteristics would be like on traction elevators, when you have a light load and the elevator is going up. Because the elevator counterweight is heavier than the car when the car is lightly loaded, the elevator motor actually acts as a little generator and creates some braking effect so that the elevator doesn't rise too quickly. You still have to address that as well. So the best thing is to stop the elevators completely before a transfer. On your subsequent transfer switch operations, after the initial life safety loads, you really have to look at what the load characteristics are. The lighting loads, you really can transfer fairly soon. The motor loads, based on how large the motors are, you may have to sequence those a little bit. The heating loads, if you've got any resistance heating that's going to go on emergency power, those should come on. And you can combine the lighting, the motors, and the heating in any order that you would like. The point is that you need to start those first rather than having your VF drives or UPS systems come on, so that you have some kind of buffer between the harmonically generated, harmonic generators such as the VF drives and the UPSs. Even if you've got filters on them, it gives a little bit of a buffer so that the harmonics don't really affect the generator quite so much. The second issue that you really have to be concerned about is the step load recovery. If you've got a large motor, say a 100 horsepower motor on a 500 kW genset, starting that motor, it really impacts the generator speed and voltage for a while, and you need to let the generator come back up to its normal operating conditions before you start anything else. And the motor starting times, if you have a motor that has a very, very high inertia load and it's not running, you really need to allow time for that motor to actually come up to full speed. So if it takes 5 or 10 seconds for it to come up to its 1800 RPM operating speed, you need to go ahead and allow that before you transfer another load. And this is a graph showing the various start times for the various generators. The top one is a typical 1800 RPM unit in a warm environment. So you have about a 1 second delay. You have 6 to 7 seconds for the generator to start and assume load. The second one is a natural gas generator. Again, you have the 1 second delay so that you don't get a lot of nuisance starting. It takes about 9 seconds for the natural gas generator that's larger than 150 or 200 kW to come up and assume load. The next one is the 1800 RPM unit diesel in an unheated enclosure where you just have jacket water heaters. In those cases, it really doesn't stay quite warm enough when you've got a very, very cold environment. And it may take 10 to 12 seconds for the generator to start and come up to 90% of its voltage and frequency. In that case, you will exceed the 10-second requirement. So that becomes somewhat problematic. If you have that same generator in a heated room and you have the jacket water heaters in there, it will easily start within your 10-second window. And the last one is a 1200 RPM diesel with a heated enclosure and block heaters, and it takes anywhere from 10 to 12 seconds to come up. And so normally you don't use a 1200 RPM or 900 RPM unit for emergency power because you end up exceeding your start time. You can't meet code with that. Back to you, Michael.
Hey, thank you very much, Ken. Those are really good tips on acoustics for generator sets and getting your switch timing right. I'm going to introduce our next speaker now, Keith Lane. Keith is the professional engineer. He's president and CEO and chief engineer of Lane, Coburn & Associates, based in Bethel, Washington. Keith has more than 17 years of electrical engineering experience and is licensed in 12 states. He's featured regularly in CSE Magazine and CSE's webcast. Keith Lane has numerous certifications, including Lead AP, RCDD, LC, and NTS, and he's active in Bixby, TPMA, and 724 Exchange. Welcome, Keith. We're very much looking forward to your presentation. You're on the air.
Hey, Michael, thank you very much. Just a little bit about Lane Coburn Associates. We provide expertise in the data center market, mission-critical facilities, provide master planning, 3D modeling, and other specialty calculations. Just real quickly, some of the clients we have, we've got data center experience all around the country. Today I'm going to be talking about proper generator sizing, total kW, compensation for harmonic load content, total required fuel capacity, and then I'm going to end up with some additional information on proper grounding, design and specification of proper grounding for systems. So typically a generator is specified with a kW rating and an associated power factor. And typically we see a power factor of 0.8. And because in a mission-critical facility we typically feed loads that are at least a 0.9 power factor or greater, you're going to run out of kWs before you use all the kVAs. So from the standpoint of just big picture conceptual sizing of generators, you want to focus on kW, not so much kVAs. But together these values, kW is the real power and kVA is the apparent power. And the engineer must consider both the engine and the generator individually as a system when designing and specifying the generator. The engine produces the real kW, or the real kW or horsepower, and controls the frequency, and the generator changes the mechanical energy into electrical energy, kVA, and must satisfy the magnetization requirements, or the kVAR, within the electrical system. So here's a little chart that just identifies the difference in the relationship between kVA and kW and power factor. When the voltage and the current are completely in line, you have unity power factor. This chart shows a purely inductive load where the current lags the voltage by 90 degrees. So you're going to be somewhere in between the unity power factor and purely inductive load. Typically in a data center you're going to be in the 95%. Oftentimes for conceptual calculations we'll sometimes assume unity power factor. But always keep in mind there is the difference between kW and kVA, and the relationship is shown there. So critical parameters when actually sizing a generator. Oftentimes the more critical parameter for sizing a generator is the starting kVA or the starting kW. And the starting kVA is going to also be dependent on the maximum allowable voltage drop during starting and will be lower for sensitive loads. So oftentimes for non-sensitive loads, you could go up as high as 30% voltage drop during starting. But for sensitive loads, you typically only want 20%. And then there are specific codes, specifically for fire pumps, for instance, that require no more than, or allow no more than 15% voltage drop. So you're going to have to oversize your generator more if you have a higher impedance generator and you have allowances for maximum voltage drop within your system. So even more additional critical parameters, SCRs or silicone-controlled rectifiers are used to chop AC waveforms and will provide nonlinear waveforms within your system. The nonlinear waveforms will cause voltage distortion across the reactor of your generator and then can cause unacceptable transient performance within your complete system. So if you have a load that creates total harmonic current distortion when you're under generator power that has a higher impedance than your utility power, that total harmonic current distortion will cause total harmonic voltage distortion, which adversely affects your entire system. To compensate for voltage distortion from nonlinear loads, a larger generator with reduced impedance can reduce the effect of the nonlinear load. So just remember, the voltage drop and the voltage distortion will be much higher in a facility when you're under generator power than under utility power. The typical generator will have anywhere from 15 to 20% or even higher internal reactance, internal impedance, or what we call subtransient reactance. When you're under utility power, you're typically around 5%. So you can see that when you have higher current distortion within your system. As that crosses between the impedance of your generator, you're going to have much worse voltage distortion within your system. So as a specification item, we typically will specify for critical environments 12% subtransient reactance or less. Of course, the less being better. And we're seeing generator manufacturers seeing this more and more in specifications. Several years ago, we used to have actually a hard time actually getting a generator, large generator. I'm talking the 2 megawatts and larger generator size, actually getting 12% subtransient reactance or less. But in some recent jobs, we've been able to get to 12%, even less, even as low as 7%. So again, the lower the subtransient reactance, the better. The lower it is also, it more mimics what you get from the utility power. So what I've got here is what you typically see in the specification. You see here the X prime D is a subtransient reactance, and it's, in this case, happens to be 0.119 pu, which would be 11.9% subtransient reactance. So one of the first things that I look for in a generator submittal is to see that type of subtransient reactance, 12% or less, especially in a critical environment where you're really relying on the generator and you're going to be serving some critical loads that do have harmonic distortion. And, to kind of talk a little bit about what Ken was talking about, when you're loading up and when you're sizing your generator, there are means and methods to provide stepping of loads within your generator. If you turned on all your loads at one time, you would have a massively oversized generator to compensate for that starting inrush. But oftentimes I've seen engineers assume, 15 or 20 steps within their system, but then they've got no means of actually providing those steps. So whatever assumptions you make on the steps for stepping on your loads when you're doing your generator calculations, just make sure that within your system you can actually do that. And one easy way of doing that is to do that with your automatic transfer switches. So if you've got a generator that's feeding life safety load and standby load and optional load, typically those will be on, well, they have to be on different ATSs, at least the life safety load. So the life safety load has to start within 10 seconds, and then the standby load within 60 seconds. And then the optional load, it can obviously be as long as you want. So here's a one-line diagram that depicts multiple ATSs. 2 of them happen to be for fire pumps, and then these would be life safety and optional loads. So again, just, a word of advice, when you are sizing your generator, you're working with owners that want the smallest generator possible because we all want to provide the most economic system as possible. But I've seen engineers, do their calculations based on 10 or more steps, but then when you drill down, they've got no justification how they could ensure during an actual emergency situation that the loads would actually step on in that manner. So the next thing I want to talk about at this point is generator fuel supply. A good rule of thumb that I'll often use is about 0.07 gallons per kW per hour. So for instance, on a 2,000 kW generator, you would be burning about 140 gallons per hour at full load. Now, on the fuel tank, whether it's a sub-base tank or a separate tank, you typically can't use more than 80% of the fuel. But for a good rule of thumb, I still use this calculation because 0.07 gallons per kW per hour assumes full load. So you're banging the generator out at full load. So it's a good rule of thumb. You can use 80% of the capacity of the fuel tank, and you're probably going to be running about 80% of your generator load. So there could be certainly a long dissertation about the different fuel tanks, but typically we see in our industry UL 142 single wall tanks, designed for the storage of flammable and combustible liquids, either because the jurisdiction requires it for larger tanks or because the owner requires it. We're seeing more and more UL 2085 tanks, double-walled interstitial tanks, and you can see some of the additional requirements of these 2 hours at 2,000 degrees, maximum average temperature of 280 degrees Fahrenheit, and So for our larger critical facilities, we're typically seeing the UL 2085 tanks instead of the UL 142. Of course, the UL 2085 tanks are going to be more expensive. So another critical thing with generators is proper grounding, proper ground fault protection. And there are typically two main methods of grounding the generators. If you supply a 4-pole ATS, you would tie the neutral and ground together at the generator and you would call it a separately derived source. This is a preferred means of grounding your system. If you have a large enough generator where you have 1,000 ampere-acre at 480 volts and you're required to have a GFI, the ground fault of your generator is going to work better with a 4-pole ATS. Also, if you have situations where you have multiple ATSs in your system, if you don't have 4-pole ATSs, there are certain situations where you can take out the GFI and actually have a situation where you have a ground fault, and depending on the settings, the ground fault may not actually trip. This is a situation where we have a 3-pole ATS where you're not actually switching the neutral. In that case, you do not tie the neutral and ground together at the generator, and it is not considered a separately derived source. This is a less expensive means of doing it, and some of our clients are using the transfer pair breaker within the switchgear, not a separate ATS. Especially when you get into the larger generators, 2.5 megawatts, and you got 4,000 amp switchgear, we're seeing kind of a trend more to this type of transfer pair. And when you do that, you have the 3-pole ATS. And if you have a 3-pole ATS, there's just certain things you need to be aware of. This is kind of a complicated wiring diagram, but what we have here is on the right side, a standby generator. On the left side, customer transformer. And in the middle, we have our main switchgear that reflects your 3-pole ATS or breakers that are 3-pole and are not switching the neutral. And there are certain circumstances, for instance, where the generator is providing power to your system, and you have a downstream ground fault, and the ground fault comes back through this red arrow, comes back up through your system, comes around, and where you actually tie your neutral and ground together at your main service, the ground fault will travel through that and make its way back to the generator. So there are certain circumstances where you have a ground fault when you're under generator that will trip the ground fault breaker, main breaker, and you could, then the generator main breaker would trip, utility power comes back on, and your utility main breaker is tripped under a ground fault that occurred when under generator, and you wouldn't know it. There are ways to mitigate that. One of them is to set the ground fault of the generator lower than the ground fault of the main service, and you would certainly mitigate that from happening. So here's another subject on grounding that could certainly be a long topic, but modified differential grounding systems. When you get into more complicated mission-critical facilities where you have multiple sources and you have 3-pole transfer switches, especially if you have circulating neutral currents like you may have in some of the newer data centers, 400-volt systems, and you have additional source grounding. The additional source grounding cannot be controlled. You have to provide ground fault selectivity even at very complex systems. And that's where you get into a modified differential grounding system, and every system is different, kind of a custom deal, but it's just something out there. If you do get involved in a system, even if you have a main-time-main situation with main board, you have to look at modified differential grounding systems. Probably much too complex at this point in this conference or this webcast to go into, but just be aware. You get into some of the more complicated data centers where you have multiple sources. You require a modified differential grounding system just for your grounding system to work properly. So, again, thank you very much. I want to pass it back to Michael.
And now we're ready for your questions. First question is going to go to Ken Lovorn, since you were the first speaker. And that question is from Jerry Inzer of Freescale, and he's asking, On a large step load, we have a voltage dip around 20% and takes 5 to 6 seconds to recover back to 90% after running a few minutes. Large step load is no problem. Is this just a cold start? Just from a cold start? Can you shed some light on that?
Yeah, I think that's typically what you see. It's according to how big the load is and compared to the generator, but that's a good place to start.
Okay. The next one's from Angela Templin from Gray and Osborne, and she's asking, is there a thermal concern with the supports for the muffler, threaded rods with vibration isolators, connecting the hot silencer and exhaust piping to the structural framing, which might be made of wood?
As long as they're fairly long and compared to the diameter, so if they're, say, a foot long, I really don't see any problem. There's probably more heat radiated from the silencer itself than there would be transmitted up the threaded rods. And so if the wood gets hot because the muffler's too close, then you need to make the threaded rods longer or move the roof up or something.
Okay. This next question might be a little out of scope, but see what you can do with it with a short answer. It's from Mike Server asking, Seaver from Caterpillar asking, has Ken had any experience in paralleling generators within the 10-second time limitation, not just starting, but paralleling? Ken?
Well, when you get a start signal and you've got multiple generators that are going to be paralleled, all the generators get the start signal at the same time. The first unit that is up to frequency and voltage transfers to the paralleling bus, and then all the other units will synchronize to that. With today's very, very accurate digital governors, sometimes it's a little difficult to get the generators to shift enough so that they can come up to the right frequency, because if they don't transfer within about 10 or 15 degrees, you start having some problems and transferring out of phase. But normally, they all transfer fairly quickly once they all come up to speed, and they all start about the same time. So they'll start in about 5 or 6 seconds, 7 seconds, according to how big they are.
Okay. And
I'd actually like to add to that. I was involved in some pretty rigorous testing on a recent project, and if you're concerned about life safety, you have to ensure that the generators require load start and sync and transfer within 10 seconds. And we ran a number of tests on a 3 parallel generator system, and almost always the first generator started and synced within about 7 or 8 seconds, and actually one time out of about 30 tests we were actually able to get all 3 to start, sync, and transfer. But you start to get over one generator, and you can't really ensure that more than one generator can start and sync within 10 seconds. I think the average time for 3 generators was about 25 to 30 seconds.
Okay, very good. Keith, I'm going to send you a question, and it's going to come from a couple people wanted some clarification about UL 142 being for single wall or double wall. You added a single wall in your presentation.
Yeah, and actually UL 142 does offer single wall and double wall constructions. Okay,
good. Keith, the next question is from Alan Stevens of Siska-Hennessy, saying even though you are assuming 0.07 kilowatts per hour fuel consumption, gallons per kilowatt hour fuel consumption, what value are you looking for as a real fuel flow from and to the generator from the day tank to address fuel injection pump cooling and the like?
Well, I mean, that's a very specific question that would be done for, you'd have to look at it on a specific project. But the actual burn of a generator at full load, based on large generators that we see in mission-critical facilities, is about 0.07 gallons per kW per hour. So his question is pretty specific, and I wouldn't be able to provide just a general answer to that.
If I could throw in something here, I've had some experience specifically on this question, and the rule of thumb that I've used in the past was somewhere between 4 and 5 times. So if you've got 0.7 gallons per kW per hour, you'll multiply that by, say, 5. And if you have a little bit of excess fuel, it really doesn't make any difference. because it just goes back to the day tank. It returns, and really it ought to return to the main tank, because if it returns to the day tank and you get a lot of recycled fuel, the fuel temperature goes up. And if you've got a small day tank and a large generator, your fuel gets too hot. So it really should circulate back to the main tank.
Okay. Very good. Thanks, Ken. A follow-up question on the day tank from Jay Sacker from EECS asking Keith, is there a formula for sizing the day tank?
Well, that's more of a mechanical function and the flow of the fuel. I've done both jobs. Sometimes, depending on the location and the amount of fuel required, we'll provide a small day tank and then a large tank outside. I don't have a specific formula for sizing the day tank, though.
Okay, very good. Keith, another question for you from this one from Jim Zavidil from KRS Engineering asking, if you don't have ground fault protection in your system, is there any reason or advantage to using a 4-pole ATS?
So usually you don't have a ground fault in your system if it's a small system. For a generator, for instance, if you have a large enough generator, say 750 kW or larger, you've got a 1,000 amp breaker, which requires a ground fault. So in order for the ground fault to work properly, you need a 4-pole ATS. Also, if you have multiple ATSs in your system, if it's not done properly and you use 3-pole ATSs, you can have problems. So I would say from a cost standpoint, if you don't have ground fault within your generator system, probably utilize a 3-pole ATS. If you're in a large enough system where you have a GFI on your generator, I would look at a 4-pole ATS. If, because of the project and the cost savings, you want to use a 3-pole, just be aware of the issues and try to compensate those issues through your selective coordination studies.
Okay. Kind of a related question. This one from Ivan Gonzalez from Arcadis asking you, Keith. We don't usually provide ground fault tripping on an emergency generator. The discussion went around settings of the genset ground fault breaker lower than utility. Please explain.
Yeah, so my reference was in the mission critical facility where you have to provide ground fault trip. In a emergency situation, if the generator was emergency, then it would just be ground fault alarm. You are correct. So in that situation with ground fault alarm, you would not be able to mitigate the potential problem of a 3-pole ATS by making the setting on the generator smaller. But on a mission critical facility where it is ground fault trip, that means of providing an avenue of mitigating that problem would be applicable.
Very good. The next question is going to go to Ken Lovorn. This one from David Pollock from BSEG LLC, and he's asking, who sets sound level requirements for installation and where can they be found? Ken.
As far as I know, there's not any specific code requirements. Really the target is you need to not exceed the sound level of the ambient conditions under the worst case operating point. So if you're in the middle of the country and it's a rural area, at night it's going to be pretty quiet. And so if there's any chance of you're disturbing anyone out there, you have to go with the worst case. If you're in the middle of an industrial complex and the sound level is 85 dB under normal circumstances, then you really don't need much attenuation. So it really is dependent on the environment and who you might disturb.
Ken, if I could add on to that, there are federal requirements and then there are local requirements, and typically it depends on your property line and who you're adjacent to. So for instance, if you're an industrial facility and you're adjacent to another industrial facility, you may be able to have 65, 70 decibels at the property line. If you're industrial to commercial, that drops down to 60, and if you're a resident in close proximity or at the property line, it's 55. So there's a whole number of requirements to go into actual sound mitigation. Typically you have an acoustical engineer who, if you have a complex project, but if you're far away from the property line and you're in an industrial to industrial, you may not need any sound mitigation at all. If you're very close to the property line and you have residential, you may need very expensive sound mitigation.
All right, very good, thank you. Ken, more on Keith. Ed Kaminsky from AMC's Engineers is asking, why do you suggest the use of 3-pole transfer switches with larger gensets?
Well, I'm not necessarily suggesting them. Many clients When you get into the large sizes, say 4,000 amp, you can provide your transfer pair via the switchgear with 4,000 amp breakers, or have a separate large automatic transfer switch. So certainly the less expensive means of providing a transfer is to provide a transfer pair for your breakers. Breakers are going to be 3-pole. So we see a lot of clients using 3-pole ATSs in large mission-critical facilities, and that is certainly okay. You just have to be aware that you will not call your generator a separately drive system, and you have to be aware of some of the potential consequences of doing that. But the superior method is to provide a 4-pole transfer.
Got it. Quick question to you, Ken. What should the minimum room temperature be? This is from Dan Lieber from AECOM.
We generally try to have the room temperature somewhere in the 60-degree range as a minimum. As you get colder, the oil, of course, thickens up, and it's going to slow the engine start time down. So you don't want to delay it or have the delay as small as possible due to the temperature issues.
Got it. And Kamel Goes from AD Engineering is asking you, Ken, what steps are you talking about? The steps that you are talking about should need separate ATSs for stepping of the loads? Question mark, question mark. So
well,
go ahead.
Yes, that's true for some loads. Specifically, if you have a number of motor loads and you have all the motors connected to a single transfer switch, you can have small timers for each of the motors so that when you transfer let's say the entire motor control center to emergency, then you can have the motors start individually as soon as they see power. The timer can start. You can set those timers anywhere you want. And so for one transfer switch, you can have, 20 different steps if you wanted to.
Okay, very good. Next question is going to go to Keith. Keith from Tron from U.S. Department of Veterans Affairs, asking, do you recommend high-resistance grounding for emergency standby generators in mission-critical operation? I think you already answered that, but if so, go ahead and elaborate it one more time.
Yeah, I think this is a new question. We
okay.
typically see, if the generators are at 480, we don't see the high impedance grounding system or low impedance grounding. In the 15 kV size, that's when you start seeing the high impedance grounding system. It's for protection of the generator, and also what it does is it allows, if there is a fault, it allows you to have an alarm and not trip your system. There's higher end engineering involved. You have to ensure that, for instance, your impedance is not greater than your charge current of your system. Your transient voltage surge suppressors will work differently. So we've seen it both ways in the higher end kind of tier 3, tier 4 type data centers utilizing 13.2 or 12.4/7 generators. We've seen the high impedance grounding systems, and they certainly do have their advantages.
Great. And Jason Harrell is asking you from Integra Telecom, should a neutral grounding resistor be used in a system with generator backup to help with reducing faults?
So that's a similar type question. You have, so basically you size a neutral ground resistor, so when you have a fault, a solidly grounded system, which is 99% of what you see when you have a fault, solidly grounded, so it produces enough current to trip the breaker. With a high impedance ground, you size it to a certain amount that you will only have, say, 5 or 6 amps running through your fault, which will not be large enough to trip your breaker, but will be high enough to trip an alarm. Just a little more complex for design, but yeah, we see those in higher end data centers with high voltage generator systems.
Okay. Ed Kaminsky from AMC's Engineers is asking Ken Lovorn, generator starting time is based on 1 megawatt. Can you give rule of thumb for gen sets 500 kilowatt or below?
Well, generally, because the rotating mass is smaller, they'll start a little bit faster, but the ignition time, it's still a diesel generator, and it's going to be pretty close. You might save a second or two if, say, you had a 250 kW gen set instead of a 1 megawatt.
Okay. And let's see. Still got some questions here. We're going to get one from David Theus from Pfizer asking, performance testing under NFPA 110, life safety level 1. Are you required to perform reactive and resistive load bank testing? Keith?
So that's a good question. Typically in mission critical facilities where we're not looking at NFPA 110, we typically provide just resistive load bank testing, especially in the size of load banks we're looking at. Resistive and reactive load bank testing can be done, but it's much more expensive. So most of the facilities we're working on are the live testing. If the mission critical facility is tested under live load, we'll have real resistive and reactive loads, but the load banks that we're seeing are typically just resistive load banks.
Okay, good. I got time for two more questions. Another one from Datron from U.S. Department of Veterans Affairs asking, is a 15 kilovolt generator listed for emergency life safety use available in the market? Kind of product question. Keith?
You know, that's a very good question. Usually when we're sizing generators for mission critical facilities, we go through one ATS and we serve all of the required load, basically the entire load of the building. And then in addition, for instance, on lighting, we will put battery backup because the ATS for that generator would not be compliant to feed emergency load, even though the mission critical emergency system or optional backup standby system is probably more robust than an emergency type system. So long answer to say that we, in our type of occasion, we provide 15 kV generators and we don't use them for emergency life safety systems. So I do not know that answer.
Okay. Ken Lovorn?
Yeah, I have never seen one. The problem that you get into is the the largest transfer switch that you can get is rated at 600 volts. If you start transferring voltages higher than that, you have to have some sort of multiple breaker scheme, and that's really not legally a transfer switch. And so I think I agree with Keith that I wouldn't see that for life safety loads.
Okay. One more question. This is kind of might require a longer answer, but that's a good one to end with. Okay. From George Matsis from Group 8 Engineering, he's asking, to either or both speakers, comment on traditional ATSs versus paired circuit breakers, i.e. cost, reliability, maintenance, etc. Do you guys have any opinions about that? ATSs versus paired circuit breakers.
You know, we're seeing more and more people utilizing the circuit breakers as the transfer pair. The issue with that is unless you're using 4-pole breakers, which I have not seen in the circuit breaker transfer pair, you can't get a 4-pole ATS. So the cost is less for certainly for just integrating the transfer pair into your switchgear.
Ken, any thoughts on that?
Well, actually, there are 4-pole breakers in some of the insulated case breakers and the power or circuit breakers, so you could pair them, but that's sort of a Rube Goldberg kind of application, in my opinion. That you have to. It's a very, very sophisticated control system, and you're just asking for potential problems. When you've got a transfer switch, that's on the same shaft. Everything is connected together. And so when you disconnect the normal side and you connect the emergency side, that all sort of goes together. The only exception is when you have the delayed transfer switches that some manufacturers provide so that you can have a delay between opening the normal and closing the emergency. But still, they're manufactured specifically for that. You actually have to put together some kind of control system to make sure that the normal is open on the breaker before you close the emergency. Otherwise, you connect the two of them together, which is a really bad thing.
Okay, very good. Well, that's all the questions we have time for at this point. I just want to close by thanking our speakers, Keith Lane and Ken Lovorn, for taking the time to share their knowledge and expertise with everybody. I'd like to thank our sponsors for sponsoring this program, making it possible for so many of you to enjoy this webcast. And I'd like to thank Consulting Specifying Engineer and On24 for presenting this event. And my name is Michael Ivanovich, the president of the Ivanovich Group in Oak Brook, Illinois. And I'd like to thank all of you attendees for taking the time to visit with us today. So on that, ladies and gentlemen, thank you very much, and we'll see you again soon. Bye-bye.